Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, thank you for coming. I'm very happy to introduce Gregor Richards, who's going to be talking about JavaScript benchmarking. Gregor is a graduate student at Purdue University working for Jan Vitek. Gregor did some really interesting work earlier this year, which was published in PLDI, on measuring the characteristics of JavaScript programs, web applications such as Facebook, Gmail, etc. And he's continued with Ben Lifshitz and I this summer working on an internship project where he's created benchmarks, which he's going to be talking about. Some interesting things about Gregor. One thing, you can choose what hat he wears at usemyhat.com. So go and choosemyhat.com. Is that right? Yeah. So go there and you can express your hat preferences to him. Otherwise, Gregor is a very interested, really interesting person in terms of dynamic languages. So if you have any questions about implementation of JavaScript, etc., he's a great resource. So please welcome Gregor Richards.
I'm glad that my hat-choosing website got higher billing than any technical abilities. Okay, so the name of this project is JSBench. Obviously, it's making benchmarks for JavaScript. So, like he already said, this is work done between the Bens here and myself. So, to some people, it's not obvious why we need JavaScript benchmarks so much. Well, JavaScript is popular, extremely popular, actually the only choice we have for web programming. There's nothing else. There's Flash, but it doesn't integrate into web pages. There's Silverlight, which also doesn't really integrate into web pages. JavaScript is how you actually make web pages dynamic. Web pages are having more and more behavior, having more and more JavaScript, essentially. Facebook is just one example of sending megs of JavaScript code during some interaction with Facebook. And all of the browsers are competing to have the fastest JavaScript engine. We, of course, know that Chrome has been really fighting to say they're the fastest. Now the IE9 team here is ramping up, and, well, all of them are sort of having these battles. So what we already know. The JavaScript benchmarks that are out there are terrible. There have been projects here, JS Meter, and projects at Purdue. This is the one that was referred to before my talk, Dynamics of JavaScript. And without going into an enormous amount of detail, suffice it to say that the behavior of JavaScript benchmarks isn't even remotely similar to the behavior of real JavaScript pages in terms of how the garbage collector acts, in terms of how objects are accessed, in terms of what kind of objects are used. There's just virtually no similarity. And real web pages are also terrible. They're terrible because they're using objects in crazy ways that make no sense. You can't look at them and say, oh, this is basically like a class-based program. I can understand this. There's no useful static analysis. There's no useful anything, really. They're just doing insane things. But they're not terrible in the same way. The benchmarks are terrible because they're unrepresentative. The web pages are, well, they're just terrible. So how do we know that these optimizations that all the browsers have been working on actually work on real web pages, when we can only test them on the benchmarks that are out there? Well, we don't. So what do we do to fix this problem? What we have done is turn web pages into benchmarks. So we know that the web pages are having the behavior that we want to test on the browsers. So make them the benchmarks. Basically, our technique is record and replay. So we record some interaction with a web page, we create a replay of that same interaction, and then by making sure that replay is deterministic and doing the same thing on any browser, we can run that in multiple browsers and just see how long they take. So the framework for recording, this is your standard, user accessing the web to start with. So there's a user, the user interacts with the browser, and the browser interacts with the web. What we do to record is inject a proxy between the browser and the web, which generates instrumented JavaScript. That instrumented JavaScript records all of the behavior of the page and creates a log. The log is then sent back to the proxy. Since we have a log, to create a replay, we can take this log file and create JavaScript code, mirror the original web page, and add some instrumentation to hook it up to the replay JavaScript code, as well as to eliminate the user from the equation. When we hook them all together, we have a replay page, and now everything is self-contained. The browser talks to a replay page. There's no interaction with the user. There's no interaction with the web. Everything is controlled. So this will be a brief running example of sort of how this process works in more detail. This is just a very simple bit of JavaScript code that creates an onload handler. So this will fire when the page is loaded. And all that onload handler does is look for an element in the document called input and then get its value. So input might be a text box, in which case the string contained within it would be assigned to my value. So this is an example of how the browser and the runtime environment for JavaScript and JavaScript, the code, might interact running that example. So eventually the page will load, and then an onload event will be fired by the browser. It's had an onload handler registered with JavaScript, so it knows to call that. The onload handler is going to call document.getElementById input. Well, document is handled by the browser. So now this goes back to the browser, and it's going to look through its model of the document and find that element. Box it up into a JavaScript object so that the JavaScript code can interact with it. And now that's going to look for the value from that object, which again will jump over, inspect the element, get that value, and in this case, this was an input box with the string hello JavaScript. Now, it's in this interaction that we can add instrumentation. So the first thing we want to do, because the document, the object called document, is the primary interface with the browser, we want to wrap that up so that all the interaction with it is controlled. So when onload is called, we want to log that that happened, log that a handler was called. We're calling a function here, so we want to log all of the arguments to it. We want to log that this object was the return from that and wrap it up, since we want all of its members to be logged as well. And then when we get the value, that'll be logged too. So to look at an actual log of this, so like I said, the first thing is that the document object, which is window.document, is assigned to, this is just some internal replay object. So obj1 will be recreated by the replay. Now, an event was fired, onload handler, and the argument to that event, in this case, is window. Now, it's trying to get the member of object1. So this is document.getElementById. Document, we've assigned the ID object1 as a memoized object. So it's trying to get the function getElementById. Well, we're going to create a memoizing function for that too, called function1. The return value of function1 is object2 when given these parameters. And then object2.value is the string hello JavaScript. So this is a fairly simple log that might be generated by our framework. Then we can take this log and turn it into replay code. So the replay code is a giant function, replay. And essentially, we're going to create the objects exactly as they say in the log. So this is line 1, window.document has that shape. Now, everything that comes after an event are parameters for the event, so we need to do them before calling the event. So number 3 was getting the function that is a member of object1. So we just create that function. Now we're creating a case for the function to return this new object. Then this final value, well, this is just a string. We don't need to wrap it up, so just put it in as a string. And finally, now that these are all set up, we can call the original onload handler, and it'll see all the right things. So we have a replay function. All we have to do is hook that into the original page with a little bit of instrumentation and time its execution. Well, there's a lot more to it than that, of course. So browser events, JavaScript doesn't give us any real notion that this function is an event. This function is an event handler, that is, and this function is just a function. Any function can be registered as an event handler, hypothetically. So effectively, we need to check in every function, was this used as an event handler? Luckily, this check is simple, because if it was an event handler, then we weren't called from JavaScript. If it was not an event handler, then we were called from JavaScript. So we just need a global Boolean that says, I'm currently in JavaScript, and if I'm not, well, now I'm going to log what the parameters were to this event, say that I am in JavaScript, and then call it again. So we have to memoize the arguments, and in most cases, just memoizing those arguments works. However, like I said, any function can be an event handler. which is to say even a closure can be an event handler. When they are, effectively all the closed variables are now parameters. We can't name an individual closure. There could be any number of them created by the JavaScript code. So essentially these are all becoming parameters. So it seems like the obvious solution is to do what we've already been doing. Well, we're going to memoize all of the closure context and then create mock objects. That's what we've been doing for everything else. Sounds like a great solution until you memoize everything in jQuery and create a mock object that does nothing. And now your entire replay is doing nothing. So that was a bad idea. Well, no, it was an okay idea. The intuition here is only if the closed variables actually change do we need to feed them back in at replay time. Do we need to recreate them? So how do we know if they change? Well, we have a recorded trace. We saw everything that happened, so we know if they're going to change. We know the future. So all we have to do is go over that trace and check, was this the same value every time? If it was, then we don't need to feed that back into the closure. There is one further complication to this. So in this case, we have a special handler function that actually registers handlers. And you'll notice this anonymous function here is the actual handler, but this is also a function. So we're actually closing over a closure, and so effectively closing over all of its closed variables as well, which means we have to log all of those contexts too. And we will get back to that. So that's how we handle events. Now, the whole idea behind doing record and replay is to hide the non-determinism of a page, to have a deterministic replay that we can compare between browsers. But there is no canonical list of all of the sources of non-determinism in JavaScript. Even if there was a canonical list, it would only be for one browser, and every other browser has its own canonical list, or non-canonical list, as it were. So really all we can do is trial and error, add things that turn out to screw us up, and then test it and make sure that it actually is producing the same behavior on different browsers. This is what we memoize right now. So, well, this is what we memoize ultimately. So there's document. This is your access to the document tree. Navigator gives you information about what browser you're running on, the user agent and version. Location is the actual URL, so obviously that needs to not change. Math.random, well, if it's going to be using random numbers, we'd better give it the same random numbers during the replay. Date is how you get the current time. And so if it is dependent on the time or the amount of time that it takes to do things, then this needs to be memoized. XML HTTP request is how JavaScript code can make web requests. So we don't want it to be making those web requests again. We just need to memoize what the results are so that the JavaScript code can run alone. And we have to prevent it from registering events. So it can't call set timeout, it can't call set interval, it can't call add event listener, attach event, anything else that has to do with registering event handlers. So this is everything that's captured by the framework. The memoization technique, yeah, oh, sorry, yes.
Can you also handle DOM-level zero event handlers?
So we handle them in that we see them. And another layer of event registration is that the keywords onload, on click, on everything are also sort of blotted away. So in that case, we're not actually calling a registration function, but we're still preventing it from assigning them as handlers and just calling them from our framework.
That's done when you parse the HTML? That's done when you parse the HTML?
That's done in the instrumentation. Oh, right, okay. So the ones on the HTML are just prevented by, well, suffice it to say, it's more complicated than that. So we have to go through the document and put on canceling handlers for those, and hope that they don't run. The ones that are done from JavaScript, we can just prevent. Yeah, it is done, yeah, but it's a bit more detail than is necessarily worthwhile to go into here. Okay, so the whole fundamental technique is memoization. Luckily, JavaScript actually makes memoization fairly easy. So we can mark the objects we want to log by wrapping. JavaScript doesn't have classes, so we can just sort of throw arbitrary data onto the objects. Hooray! And then, with this instrumentation, remembering this is record time instrumentation, so the amount of time it takes to run isn't hugely important, just take every member access, so x.y, and turn it into this complicated function, memoized read, of the object x with the parameter y, which returns a new object that you want to get the parameter y off of. So memoized read guarantees that if x was a memoized object, then anything it returns will either be a memoized object or a function that memoizes its return values and such. So this is sort of what guarantees that no matter which of these interfaces you start accessing memoized objects through, everything that you ultimately get to will also be memoized. Right, so we're handling this simply by, well, the objects are wrapped, so we're wrapping members if those come out. And then if that member is a function, we create a new function that logs its return value and wraps that as a memoized object as well. So I've talked about a lot of logging. And at this point, what are we capturing? Well, we have those initial sources of non-determinism, math.random, document, that kind of thing. We have the arguments to the event handlers. We have the closure context of the event handlers. We have the closure context of anything that's closed over by any of these other things. Well, that's a lot of data. That's actually an enormous amount of data. That's megs of data. So we can't just take those enormous logs and create a huge replay function. It would kill just every browser. So we need to strip out the things that we don't need, such as variables that don't change in closure context, and the things that we don't want. So for example, we can remove the memoization of the document object and then allow the replay to access the document. Or we can leave it in and make the replay sort of more pure JavaScript. That's done by abstracting the log and then doing pruning. So this is the same log as before. We have window.document as a member, and then we're getting getElement by ID and getting the value from that. Now we've taken these three and said, these are actually being performed by this event. So all we've done is made them part of the event. Now to prune this, first we need to check all the dependencies. Well, that's simple. We know that object 1 is used here, and we know that it's a dependency here. We know that object 1 is used here, and that the function returned by this member is used there as well. And then the return value of that is used here. So to remove window.document, for example, we can remove this, and now we know that it will never get object 1. So we don't need to do anything to make object 1 have the right shape. Well, then we don't need to do that. But now we know it'll never get function 1. OK, then we don't need that. And now we know it'll never get object 2, so we don't need that. So this is all done just by an abstraction and pruning framework. This example was removing the DOM. But this is also how unnecessary closed variables are removed. Anything else that we want to remove potentially is removed from the log. So we can create 4 replay modes by turning on or off the access to the DOM and turning on or off actually using browser event dispatch. They each have their own disadvantages. If we turn on the DOM, well, this is a way that you can get to the browser, and so the JavaScript code will ultimately be able to tell what browser it's on if it wants to. So if we turn it on, then we have that problem. If we turn it off, then, well, it's not really touching the browser. Event dispatch, well, normally event dispatch is done by interaction with the user interface, and that's great, but we can't actually reproduce that interaction. So we have to use this mechanism that's normally used sort of for testing and some very strange APIs. And it's very uncommon in real code, so it's not very representative. Disabling both is arguably unrealistic because now the browser isn't dispatching events. It's not accessing the DOM at all. This is just pure JavaScript code. Is that really what the page was doing? OK, a quick demo. So essentially, we've captured all these pages and wrapped them up into a simple benchmark harness. So this first one is a simple game. It was the first thing we did because I control the code, so it was really easy for me to change it. You can see that Amazon is also memoized. This changing on the left is whether it runs in DOM mode or non-DOM mode. So in DOM mode, it's folding those menus in. In non-DOM mode, it wasn't. Microsoft.com, Silverlight is disabled because that's not what we're measuring. There are a few others on here. It's probably not worthwhile to wait for all of them to run through. Right, so here's Bing. The background image isn't there, but otherwise the page is complete. And essentially, with all of these, this is economist.com. With all of these, oops, how the hell did I do that? Sorry, there it is. all we're doing is measuring the amount of time and then reporting it. Well, okay, so Amazon took 125 milliseconds in this particular configuration. Normally, of course, we would run many more runs than one in each configuration. I hacked this harness so that we could actually see everything run. Here's MSNBC, for example. So it works. That's a good property for a benchmark to have. Okay, evaluation. So here are the benchmarks we made. There are two that are not at all realistic and are, in fact, both programs that I wrote out of my own insanity well before this internship started. So subtly.us is a game. It's sort of like Guitar Hero, only with Sibelius's music instead of terrible music. JSMips is a MIP simulator in JavaScript, so that's another highly typical thing that people do on real web pages, is simulate MIPS machines. And then these real-world web pages. So Amazon, Microsoft, Bing Bing has more behavior than one might expect. Google Maps, of course, has an enormous amount of behavior. Economist.com, you would think, doesn't have much, but it's crazy. And MSNBC. So just an interesting thing to note, these aren't small. I mean, Amazon here is more than a meg of JavaScript code. Bing is very little, but does a lot of behavior, so there's no connection there either. So what are the questions we can ask to evaluate this? What is correct? Well, how does the real site compare to our replay? So are they doing the same thing? And we can look at that in terms of the JavaScript engine's behavior. So imagine the browser is just an I/O device. I don't care what the browser is going to do with this interaction. I'm just going to look at code gen, GC, how often I'm calling into and out of JavaScript, etc. And then we can look, how does the browser's behavior differ? So now, assuming the JavaScript behavior is correctly replicated, am I actually causing the browser to do the same thing? Is it doing the same number of layout events, paint events, CSS calculations, and that kind of thing? The other side of these questions is sort of how do our benchmarks, the benchmarks we've actually created compare, not to the real page, but just across browsers. So obviously how they compare across browsers, this is what everybody wants to know, right? Which browser is doing the best? And how do the different modes, adding DOM, removing DOM, adding events, removing events, affect the different browsers in different ways? This is everything we looked at. Basically, the strategy, we instrument a browser, get it to tell us the information we want. In fact, IE8 and IE9 already have this instrumentation built in. The Firefox team is also adding instrumentation for us. Awesome. And we can also add some further instrumentation to the JavaScript code to tell us when events are dispatched and that kind of thing. And then compare the events between a real site and a replay site, or between two browsers, or whatever we need to compare. This is just a list of the browsers that we use. So Internet Explorer 8, 9, both Platform Preview 4 and 3, Firefox, both the latest release, and a beta of 4.0. I did these recordings before 4.0 B3 was out. Google Chrome 5, a snapshot of Chrome 6, Opera 10, and Safari 5.0.1. So, JavaScript fidelity. The browser is now an I/O device. We're just focused on JavaScript. So run Amazon.com, run a replay of Amazon.com, as well as just going to Amazon.com, and do a few runs, see what the range of these behaviors is, try and make sure that I'm doing the same thing in the replay as in the real site. So this is calls into JavaScript. This is when the browser called JavaScript code. And this on the left is just how many times this event occurred, just a pure count. So in this case, we can see that in this particular interaction with Amazon.com, JavaScript got called some 2,400 to 2,600 times in the real site. And the real site shows a lot of variability. The replay is perfect. It's a replay. But furthermore, it's well within this range. So in this sense, we're representative. We can look at a few other things. So this calls out from JavaScript when JavaScript code causes the browser to do some calculation, or the runtime engine. This is a lot higher. It's in the 61,000 range. But again, the replay is perfectly consistent, and it's within the range. So JIT, we don't expect the replay to cause exactly the same number of jitting events. And in fact, there aren't that many jitting events that occur in either case. And the ranges don't perfectly align, but we're seeing something in the 14 to 20 JITs on both the real and the replay. Now, garbage collection is a little bit interesting. because clever browsers can do garbage collection when the JavaScript engine isn't heavily utilizing the CPU. But we are always heavily utilizing the CPU. So what we see is a reduction in the number of garbage collector cycles, but an increase in the amount of time spent in garbage collection. So the increase in time is easily explained. We're creating these mock objects. There's now more stuff. The decrease, this is probably just due to the engine no longer being able to do GC cycles in slack time. So our goal here, sorry, yes.
Which build are these numbers generated from?
This is from platform preview. This is from IE9 platform preview 4.
Okay.
Yeah. Okay, so our whole goal here was to remove non-determinism from the website. So a reasonable question is, are the websites non-deterministic in the first place? Well, we've got this whole framework. We can record all of the events that occur, for example, in Amazon again, and then connect and see sort of how much non-determinism there is. So we might see, for example, in one run, there's an onload event that fired, and then an XHR event that fired, and then a timer event that fired. And in another run, an onload event fired, and then, oh, the timer event happened first, because both of these, there's no correct scheduling of them. And then the XHR event occurred, and we can hook them up and see, oh, well, all the events are accounted for, they're just in a different order. When we do that for an entire run of Amazon, it's a lot of data. But we can break it down and look at a few different sections. So on Amazon, what we see is that at the beginning, most things are lined up. There's a few events. These were XHR events that can sort of stray from one location to another. And then we hit a point where there are just timers running crazy. There's like 3 separate timers all doing different things, plus XHR events. And you'd be lucky to get these to run in the same order ever. And then we hit this sort of quiescent state where there are no more timers running, there's just sort of interaction, and so we can cause this to be perfectly deterministic. It's this phase that we want to be able to normalize. Now, this is a comparison between the real site and the replay site. I don't have the slides for real to real, but suffice it to say we see pretty much the same thing. And if you were to compare a replay to a different replay, of course, everything would be lined up perfectly. So browser fidelity, now we're looking at Microsoft.com for this. We can look at these 3 values that are done by, in this case, from still IE9 Platform Preview 4, in terms of sort of what the browser is doing when our code is fed to it. Layouts, paints, and CSS calculations. There's a lot of other things we can look at, too, but most of them sort of normalize to the exact same value, which makes them very boring for displaying. Well, what we're seeing here is layout events were well within the range, a little bit on the low side. Paint events, yeah, we're pretty representative again. Sorry.
How is it that there are way more layout events than paint events? It seems backwards.
So, I mean, this is what ETW is reporting. I would say probably that it's cleverly only painting sort of when it needs to. It's buffering up paint events and not, like it's only doing it at so many frames per second or something like that. And so if it's just going to do a whole bunch of crazy changes and cause all these layouts, and then, bam, paint it all at once, that would just be my guess.
Like how long is this, like a 1 second?
Right, so this is Microsoft, and the Microsoft benchmark is just the load time. So actually, we'll say exactly how much time this was in a moment, but it's like 500 milliseconds or something. So
okay, yeah, that makes more sense.
Yeah. Oh, we'll say how much time it is right here. Okay, so... right, just to finish up on this. So the real time, we see these ranges. And suffice it to say, we're pretty close. We're causing similar behavior to happen. This was in the most complete mode we could make, by the way. So this is when we enable the DOM, enable events, enable everything. So here is, as reported by XPerfView, the CPU utilization in a range of events happening on the real Microsoft and on our replay. So the main thing is that there is, I think, XHR events, I don't recall from Microsoft, some events that are going to be fired on a timer. And so we do see this time compression that our replay timeline, everything is going to happen at once. But the real timeline, well, it's sort of splayed out. But this is 710 milliseconds of real time, 260 milliseconds of CPU time. And on the replay, well, this is 265 milliseconds of real time, 257 milliseconds of CPU time. The CPU time is very close. The real time, well, we've compressed it all down. So this can affect how the garbage collector behaves. It can affect how the painting behaves. It can affect all sorts of things. OK, so we've looked at real to replay. Now we're going to look at replay to replay and compare them across browsers. So we want to make sure that all of our instrumentation has prevented two browsers from doing different things with the same benchmark, in this case economist.com. So we recorded the complete call path of economist.com, all of the blocks, everything. And OK, there are 10,733 function calls in this trace of economist.com that we recorded. And that's exactly identical across all of the browsers we tested on. Hooray, so we've created consistent behavior. But you could reasonably ask, was economist.com just consistent anyway? Did we just sort of have a stroke of luck here? So I poisoned the replay, took out the navigator object, which is one way that you can check what browser you're on. And OK, we don't see enormous changes. There are only 11 calls changed on Internet Explorer and 5 calls changed on Chrome. And Firefox, which was the recorded browser, well, there are 0 calls changed. That's good. But there is a difference. So we are actually forcing things to go down the same path. Now we have different modes. So this is the speed of the DOM mode relative to the speed of the pure JavaScript mode on Amazon.com. So when we add the DOM, you're going to add some more time in because now it has to communicate through this browser boundary on different browsers. And we can see that the effect of adding the DOM is different on different browsers, but everything is fairly close to about 2x for this particular site. Now, event dispatch is a little bit more obnoxious. So event dispatch on the IE9 preview we have is fairly slow, again, using this post message mechanism, so it's not a hugely representative mechanism. Everything else, again, hovers around 2x, except for Safari, which has an amazing 77x blow up when we use this mechanism. Unfortunately, the result of this isn't a fair benchmark. We can't really use, sorry.
This is which mode, IE standards mode or?
This is IE9 standard 9 standards mode, yes. All of these benchmarks will run in standards mode. Yeah. We can also compare the absolute time. So if you recall from this slide, it looks like IE8 is paying a lot less for DOM than IE9 is. But if we look at the absolute time, no, IE8 is just paying a lot more for JavaScript than IE9 is. In terms of JavaScript time, IE9 swamps everything on this particular benchmark. But the DOM time, it has reduced from IE8, but not quite enough to catch up with a lot of other browsers. We can also compare Microsoft.com here. So because this is load time events and Silverlight is disabled, there's less DOM behavior. Now IE9 is swamping everything. And, well, we see fairly expected results. The DOM adds a little bit of time. So we ran these benchmarks just to compare how they might behave on different machines of different levels of power. So we have this sort of crummy old 1-core Pentium 4 and the beefy 8-core Xeon E5345. And the question is, not only how much speed gain are we actually going to get moving from one to the other, but are the different modes affected in different ways? So this is a comparison of Amazon.com. This is the speed up moving from this crummy 1-core machine to awesome 8-core machine. And the blue bar is pure JavaScript mode. The red bar is when we enable the DOM. And what we're seeing is, and I should mention, IE9 we couldn't run the same version of IE9 on that machine as the original machine, so I didn't put the comparison there because they aren't relevant numbers. So we see around 1.5 speed up for most browsers, and a lot of browsers are doing a little bit better with JavaScript than with DOM. But for the most part, we're seeing about the same speed up across the browsers, with Safari doing surprisingly not all that well with the different system, and all of the rest hovering around 1.5 to 2x. So another thing you could ask is, are these actually giving the same time on a browser, and are these results relevant and correct at all? On most browsers, and we can measure this by taking the standard deviation of the times in 20 runs in this case, and divide that by the mean of the times. We expect that the standard deviation will be small compared to the means. On most browsers, this is quite small. It's always less than 20%, usually less than 1%. In fact, on IE8, it never gets higher than 0.5%. And on Opera, it's sometimes more than 200%. The standard deviation is more than 200% of the mean. Oh, wait, Opera also sometimes told us that benchmarks took negative time to run. So I think that Opera's timing facilities are a little bit unreliable.
Does it
Does it run the SunSpiders fast?
Yes, it does. Or, it claims it's fast. Everything has to use the date.getTime mechanism, and if you can't trust that, then what the hell can you trust? Okay, this is what everybody's been waiting for, right? The cross-browser performance comparison. This is sort of the results of our benchmarks. So I've only shown the browsers that actually win sometimes. If we added Firefox, all the Firefox versions, they'd be up there. And if we added IE8, it would be on the moon somewhere. So these are just the browsers that actually win. The orange bar is Chrome 6, the red bar is IE9, and the sort of pinkish, puce-ish bar is a surprising contender, Safari 5, which sort of came from nowhere to beat both Chrome and IE9 on several benchmarks. But we can see that IE9 is winning in a few places, Chrome is winning in a few places. Basically, they're all very competitive with each other. Okay, what can we conclude from this? This can sort of be broken down into the academic conclusions and the practical conclusions. So we have this system. We can make records and replays of real sites and turn them into benchmarks. We have 8 large applications that we've done that with. I listed those earlier. And we've experimentally shown that it makes sense. And an interesting result is that all the browsers sort of even out when we run our benchmarks, whereas if you look at the SunSpider results, for example, things tend to splay out to 10x, 100x, insane differences. Practical results. So we'd like to hope we have somehow influenced IE9 and the Firefox team in what they're thinking about benchmarking. And we've integrated our benchmark suite into MSR's experimental JavaScript engine, so it's being used to measure our own speed. That's nice. And we're kind of hopeful that at least some of these benchmarks could be released to a wider audience soon. Questions?
Are you aware of the mugshot work done here?
Yes.
in MSR?
Yeah.
How does your system compare to that?
So we stole some code from Mugshot. So Mugshot is a good technique for debugging, but so the issue is that the way it's doing event dispatch and such is very browser specific. It involves a lot of sort of careful implementation and such. We wanted to do something that would not necessarily be as event per event accurate as for debugging purposes and such, because we're focused on making it very light so that we can do benchmarking with it. So I mean, both approaches make sense just depending on sort of what kind of replay you want. But where they overlapped, yeah, we interacted.
Is your system a subset of theirs, or you are?
No, it's just sort of distinct. I mean, yeah, it's so there. I mean, so we use this memoization approach that doesn't quite connect to anything that they did, and yeah, they aren't quite the same. But where they overlap, we've shared.
So you were saying the MSR's experimental JavaScript engine, right? Are you using the new JavaScript engine, which is part of IE9, or?
Yeah, so the MSR's experimental JavaScript engine is totally separate. We're doing experimental tracing JavaScript compilation. It's it's.
But the IE9.
Yeah, and yeah, the IE9 numbers are from are from the.
Okay, the engine is totally different engine is being developed or something?
Yeah, by MSR.
Oh, okay.
Yeah, I mean,
But
there's a
that's-
paper about it in ÜMSLA this year. It's called Spur. It's a tracing jet for JavaScript. Any questions? So, go ahead.
Do you also handle JavaScript getters and setters?
Define handle, I guess. So the way we memoize things, it doesn't matter if it's a getter or a setter, but it'll always turn into just a value for us. Anything in the original code that had getters or setters, so long as it's not something we need to touch, it'll continue to work. Basically, just the way that we're doing memoization doesn't interfere with that. So yeah, I mean, it works. It's just they're disconnected and things. Brian had a question.
So how hard is it to make a new benchmark? Just like drive by your favorite website? And
So that depends on the page. By the time I was getting to the end, so like JSMips is a terrible example because it's my own page, of course, but I didn't write it to be made into a replay. It took me like an hour, but that's on a very friendly page. On like So yeah, MSNBC was the last one I did before that, and it was kind of finicky. I would say it never takes more than like a week and a half of not, just solely hammering out code 8 hours a day. But, the system isn't quite perfect enough that you can feed any page into it and it'll just work right now, but it's getting there, and so most pages really should only take a few hours to build.
Just kind of refining your framework then, as opposed
Well, so the recent ones I've done haven't involved much refinement of the framework. It's just been, actually the biggest problem is just mirroring the site. That's so difficult to do in a way that actually works. So that's actually the biggest cost and time, getting a mirror of the site that actually works, and then actually running it through the engine. That just takes time. Not a lot of effort. It's just, recording takes time, and then producing all the replays takes time. There's nothing hugely complicated to it. There's rarely any finesse required to make it work. It's just all of these things up until the actual replay are kind of slow.
How about running it in different browsers? How difficult is it to run the benchmarks in a browser? Just go to the website.
Go to that URL and press run.
At high level, the intention is to make it as easy to use as SunSpider.
Yeah.
SunSpider, is one of the nice things about anybody can run it.
Yeah, one could argue that you could get sort of more accurate results in some sense if you were really profiling the browser and running things through Xperf or whatnot and getting the actual CPU time. But what we wanted was something that, just like SunSpider, you can go to a page and you can click run, and then you can get a number.
Any question? So, you run several sites, right? So, what is the summary finding of where IE9 stands with other browsers?
So
with JavaScript and with the DOM and without DOM, pure JavaScript.
Right. So this is the pure JavaScript results, and you can see that it's at worst very close to the others. It's beating Chrome in quite a few places. Safari sort of came from behind to be tricky. What?
Lower.
No, lower is better. This is the time in milliseconds to run a benchmark. So yeah, it's winning. It's the worst thing I could say. The most pessimistic thing I could say is that it's competitive with Chrome 6. Realistically, it's beating it in a lot of cases, and it's very, very close.
What happens when you add the DOM?
When we add the DOM, so that obviously that depends on the browser and the benchmark. What we see is that. I don't know if I have a slide that makes that very clear. Yeah, I don't have a bonus slide that makes that particularly clear. So when we add the DOM, obviously it depends on the browser and the site, but it seems like Chrome's DOM is doing better than IE9's DOM right now. So on some sites that IE9 won on normally in pure JavaScript mode, it'll now be a little bit slower than Chrome on.
Because I'm saying IE8 DOM is better than IE9 DOM.
No, it isn't. So just because of how enormous the IE8 JavaScript bars are, it can sort of appear like that as a optical illusion. But the IE9 DOM minus JavaScript time is always lower than the IE8 DOM minus JavaScript time.
And I guess one of the things is that there's a fast DOM in IE9, which is one of the latest additions.
Right.
And we're not completely clear that the tech preview 4 that's being used here was actually using the fast.
We're getting some.
PPP4 has fast DOM in it.
So we've gotten conflicting information from different people on that, and so
I guess another way to put it is we actually have an install of the IE9 from the depot as opposed to the tech preview.
Yeah.
And that runs faster than the tech preview for some reason. So
and the DOM.
It's not completely obvious why.
You can do type of window or type of document.write will say function. If it says function, fastDOM is enabled.
Okay, I'll check that.
And fastDOM is enabled only in 9 mode, standard.
Right.